So first, I'd like to say welcome, everybody. My name is Dr. Kelton McMahon. I'm a professor of oceanography at the Graduate School of Oceanography at the University of Rhode Island. And it's my great pleasure to be with all of you this evening. Happy Earth Day. And I'd like to start out by thanking the Aquidneck Land Trust and the William H. Donner Foundation for supporting this seminar series, as well as supporting a number of climate education initiatives in Rhode Island. I've been a part of a number of seminars in high schools throughout the state, supported by the Donner Foundation and the Aquidneck Land Trust, helping to educate, encourage, and empower the next generation of scientists, business people, educators, and educated voters on climate change and the world around us. So thank you all for taking the time to sit with me this evening. I'm going to share my screen now and give you a little bit of an overview of modern climate change, where we are today, and hopefully share a bit of a message of hope about where we're headed in the future. We don't often hear hope and climate change in the same sentence, but I'd like to talk a bit about how I think we can move forward in a positive way to shape a future that works for all of us. All right. How's that looking? Good? Excellent. All right. Well, thank you so much. As I mentioned, we're going to talk about climate change today. But before I get into that, I thought I would introduce myself a little bit. I think one of the first things you need to know about me is that when I was a kid, I really wanted to grow up to be Indiana Jones. I thought, he was this brilliant professor by day, swashbuckling explorer by night. He got to travel the world hunting for ancient artifacts that revealed secrets of the world's past. And hopefully, as you see through this seminar, I've actually come fairly close. I have destroyed far fewer temples in my career, but as a professor of oceanography at URI, I've managed to explore ancient systems to help us figure out how our world is changing as a function of climate and how that might impact where we go in the future. And so this is actually a video of myself. I'm the gentleman in the beard in front. My hair was a lot shorter back then. My beard was a lot longer. But we were down in Antarctica, sifting through penguin colonies, pulling out artifacts like this penguin leg bone, bone chips, eggshells, feathers, entire mummified creatures. This is actually a mummified penguin chick that's about 2,000 years old. And we use these samples in my analytical chemistry lab to learn about how past ecosystems have responded to environmental or climatic change as a way to help us learn about how future systems might respond. And so, as I mentioned, I'm a professor of oceanography at URI. My group looks at how life changes in the face of global environmental change. This is my amazing cast of students and postdocs.
He's really, really good at
And and so today I want to share a couple of messages with you. The first is I'm just going to talk a little bit about what climate is and how it's changing. And then I'm going to hopefully share a bit of a hopeful message about how we might be able to go about creating a viable climate future. And so as I'm going, please, if you have questions, feel free to unmute yourself, ask questions. You can ask it in the chat, and I will do my best to pay attention to the chat. But if you don't have questions, just please keep yourself on mute, and that way we don't get too distracted with all of the goings on in all of our various homes. Although that being said, I'm sure my dogs are going to come up and say hi at some point during this. So to start, I think it's really important to distinguish. Oops, come back. I think it's really important to distinguish between weather and climate. And so I'm going to play a little video first that from Neil deGrasse Tyson, who I think will do a far more eloquent job of distinguishing between weather, our daily changes in atmospheric condition. It might be snowy this morning and sunny and warm later this afternoon versus our climate. What is Rhode Island like, on a typical January? And so the time scales between weather, day to day, hour to hour atmospheric changes and climate, typically like 30-year averages is really, really important to thinking about climate change and why a small change in temperature, 2 or 3 degrees, has huge implications for the structure and function of the world around us.
Okay, so if we scientists are so good at making these dire long-term predictions about the climate, how come we're so lousy about predicting the weather? Here's the difference between weather and climate. Weather is what the atmosphere does in the short term, hour to hour, day to day. Weather is chaotic, which means that even a microscopic disturbance can lead to large-scale changes. That's why those 10-day weather forecasts are useless. A butterfly flaps its wings in Bali, and 6 weeks later, your outdoor wedding in Maine is ruined. Climate is the long-term average of the weather over a number of years. It's shaped by global forces that alter the energy balance in the atmosphere, such as changes in the sun, tilt of the Earth's axis, the amount of sunlight the Earth reflects back to space, and the concentration of greenhouse gases in the air. A change in any of them affects the climate in ways that are broadly predictable. My friend's meandering represents the short-term fluctuations. That's weather. It's almost impossible to predict what will attract his interest next, but not hard to know what the range of his meandering will be, because I'm holding him on a leash. We can't observe climate directly. All we see is the weather. The average weather over the course of years reveals a pattern. I represent that long-term trend, which is climate. Keep your eye on the man, not the dog. Weather is hard to predict, like my friend here, but climate is predictable. Climate has changed many times in the long history of the Earth, but always in response to a global force. The strongest force driving climate change right now is the increasing CO2 from the burning of fossil fuels, which is trapping more heat from the sun. All that additional energy has to go somewhere. Some of it warms the air. Most of it ends up in the oceans. All over the world, the oceans are getting warmer.
So, as he was talking, he mentioned the difference between these short-term fluctuations in our atmospheric condition, weather, and the patterns over really long time periods. And those patterns in our atmospheric conditions are shaped by gases in our atmosphere, like CO2. And so I'm going to play another little video just to get us all on the same page of, what's so special about CO2. And it has to do with its relationship with energy and its relationship with our climate through a process that we call the greenhouse effect.
Our climate is changing, and temperatures in general are increasing on the planet. Sea levels are rising, and the ice is melting at the North and South poles. One reason for this is the greenhouse effect. But what is the greenhouse effect? A greenhouse is normally something useful. It helps us grow things like tomatoes out of season. That's because it's nice and warm inside a greenhouse. The sunlight enters and visible light penetrates the glass. This is partly absorbed by the plants in the soil and partly reflected on the outside as invisible heat radiation. As a result, temperatures rise inside the greenhouse. The planet Earth obtains warmth in a similar fashion. Sunlight penetrates the gas layer of the atmosphere. It's partly absorbed and partly reflected, just like in a greenhouse. Small particles in the air ensure that a percentage of the reflected radiation is sent back to Earth, which is fortunate because otherwise we could not survive. Without the natural greenhouse effect, temperatures on our planet would be around minus 18 degrees Celsius, and not the average 15 degrees Celsius above freezing. However, humans cause a lot of pollution by producing large amounts of carbon dioxide, methane, and nitrous oxide. The small particles increase in number, and the result is just like a greenhouse where the glass is too thick. So an increased amount of radiation is sent back to Earth and the heat is unable to escape, causing temperatures to rise constantly on our planet.
So I think it's important to remember that CO2 is not inherently a bad compound. It's not something that we want to get rid of completely because CO2 helps make our planet habitable. It would be, well below freezing without any CO2. The challenge is how much CO2 is in the atmosphere regulates the temperature. And if we have too much CO2, we can have a massive increase in global temperatures, which alters the structure and function of the world around us. I'm not going to show too many scientific figures in this talk, but this is probably one of the most famous carbon dioxide figures ever produced. It's called the Keeling curve. We have year on the x-axis, atmospheric CO2 concentration on the y-axis, and this is recorded a monthly average at the at an observatory in Hawaii, and it's been going on since the late 50s. And what we see is this rapid increase in CO2 through time. And this is something that atmospheric chemists got really quite alarmed about, knowing the relationship between temperature, CO2, and almost all of the major functions on Earth. And so scientists for a number of decades now have been asking this question of what's causing the CO2 to increase so rapidly. And I like to use the analogy of a bathtub. You can imagine that a bathtub is filling up with water. The state of that bathtub, where your water level lies, is going to be a function of your inputs, your sources, and the removals, the sinks. For instance, right before I got here, my wife and I were giving our little 8-month-old her nighttime bath. If we've got our bath running, we've got the drain plugged up. If we don't pay careful attention and we're off doing something else, that bathtub is going to raise. And the more, if our sources outweigh our sinks, all of a sudden we come in with our daughter to start bath time and our bathtub is overflowing. And so we can do that same math in our atmosphere, thinking about CO2 and weighing the relative sources, the emissions of CO2, and the sinks or the net removals. And this is a general schematic, just thinking about how CO2 moves through Earth's system. On the right, we have a number of natural processes. So you'll notice the arrows here are really, really large. These are in billions of tons of CO2. But, Earth's terrestrial system, plants, take up and give off lots and lots of CO2. 444 to 450 billion tons of CO2. But you'll notice that if you do that subtraction, the net change in CO2 from, say, land vegetation is a sink. The plants take up more CO2 than they give off. You look at the ocean, a similarly very, very large flux or change in CO2. But yet again, the ocean is a net sink, a net removal of CO2. The challenge right now is that humans have created a relatively small in comparison change in CO2, but we don't have a comparable sink to our sources. So right now we are filling up the bathtub without an effective drain. And so the CO2 is coming from things like coal burning plants that develop our electricity, transportation, burning fossil fuels for gas, land use practices like deforestation, removing trees, which are a major sink of CO2. And so as a result, this source of CO2 from human production outweighs all of these natural sinks. And so not only is the amount of CO2 going up, but the rate at which that CO2 is going up is quite alarming. And in fact, the ocean is serving as a major buffer. So right now, the ocean takes up about 50% of all the extra CO2 we're putting into the atmosphere. and about 90% of all the excess heat. And so right now, the ocean is actually buffering a lot of the damage that could be done. And one of the questions we have is how much longer can the ocean continue to be doing the Yeoman's share of work, taking up that excess CO2? So one of the questions I get a lot is like, is this a climate emergency or is this just fake news? Is this something that is happening, throughout history, or is this something new and unique? And in order to answer that question, we know that climate has changed throughout the history of Earth. What makes this current situation unique and different? In order to do that, we need to look back through time. We need to understand how the past has changed to help us make predictions about how the future might respond. And so, one more scientific figure, because I think it's really helpful to illustrate this. Uh, this is a 800,000 year record. We have CO2 concentration in blue here in parts per million, and we have temperature in degrees Celsius here in, let's call that orange. And what you'll notice is over this 800,000 year record, CO2 has gone up and down and up and down and up and down. Temperature mirrors that pattern. So as CO2 goes up, temperature goes up, CO2 goes down, temperature goes down. But so, it is no secret that CO2 has fluctuated significantly throughout the history of Earth. The challenge we're facing right now is these changes are over relatively large timescales, tens of thousands to hundreds of thousands of years. Since the Industrial Revolution, and the American Industrial Revolution in particular, in 1790, actually was birthed right here in North Providence. Since that Industrial Revolution, there has been a massive new source of CO2 without a comparable sink. And as a result, CO2 concentration is skyrocketing. So we're now, I just checked CO2.earth to look at what the current CO2 concentration in the atmosphere is. It's about 418 ppm in April 2021. For reference, we haven't seen this amount of CO2 in our atmosphere for the last 3 million years. And so when we think about changes in CO2, we're concerned both with the amount of CO2. So obviously, this is a lot higher CO2 than we've seen in quite some time, almost a million years now, but also the rate of change. We've hit this peak much faster than the natural cycles of CO2. So the amount and the rate are what we really care about. If you want to think about what the Earth was like the last time CO2 in our atmosphere was at this high, we go about 3 million years ago to the Pliocene. So this is the east coast of the US. This dark green line is the sea level today. So this is our current coastline. Here we are, Newport. Here's Cape Cod, Long Island. 3 million years ago, when CO2 was at the current concentration it is now, Earth's atmosphere was about 3 degrees Celsius warmer, about 5 degrees Fahrenheit. Sea level rise was at least 30 feet higher, possibly even more. So this light green line is the coastline the last time Earth's CO2 is as high as it is today. As you can see, we would all be swimming right now. New York City is gone. Almost all of Florida is gone. Washington, D.C. is gone. Boston's gone. So all underwater. And at the same time, there are actually giant camels roaming the forested Arctic. So the high Arctic would actually be a large forest with giant roaming camels. So a system fundamentally different to the world that we know today. I often get questions like, how do we even know what CO2 or temperature was like, 1,000 years ago, a million years ago? And to do that, we look at really old archives, and there are a couple of different ways we can do that. We can actually look directly at concentrations of CO2 trapped in things like ice cores. So this is actually an ice core collected from Lake Vostok in Antarctica. It's a over 2 mile thick glacier sitting on top of Antarctica. And scientists here took these cores, and what these cores are of ice are impacted layers that trap bubbles. And through time, these bubbles have recorded the atmospheric conditions over 1 million years. And so they take these cores and they can take them back to the lab, and they can look at how CO2 concentrations have changed on really long time scales. We can also look at chemical cues, and this is something that my lab does. We are a isotope geochemistry lab, so we use chemistry to answer questions about Earth's climate, Earth's ecosystems. Uh, you can look at really old archives. This is an example of a giant sequoia that was cut down in California. When this sequoia first germinated, it was 900 AD during the Aztec development. Each of these lines represents major changes in our history. You know, this line is the Aztecs began building Tenochtitlan in Mexico. Here we've got 1492, Columbus is sailing to America. This line here is the signing of the Declaration of Independence in 1776, all the way out to 1930 when this tree fell down. And so these long biological archives give us chemical clues of what past environments were like. And so one of the examples that my group does is we actually look at deep sea corals as biological archives of the ancient past. These are probably some of the most interesting, fascinating biological archives that I've ever got to work on. These corals sit on underwater mountains, and they feed on organic matter that's sinking from the surface ocean down hundreds or even thousands of meters to the sea floor. And they record chemical signatures of the environment around them in their tissues. So this is actually a video that we took collecting one of these corals, where we're sitting up on a ship and we've got a remotely operated underwater vehicle, like an underwater robot that we're controlling with these joysticks and cameras to collect and put into this basket that we can then take up to the surface and take back to the lab with us. And what's really neat about these corals is if you take a cross section of this skeleton base, it looks very similar to a tree trunk. So this is a cross section of one of these corals. And this coral is almost 3,000 years old, and it lays down rings just like a tree trunk. And we can take a really high precision Dremel drill. It kind of looks like a dental drill with high precision camera set up to it. And we can mill out bands along from the outer edge, the most recent period, all the way back to this core. And we can use chemistry to answer what questions about what the environment was like. You know, what was the temperature like? What was productivity? How much food was in the ocean fueling these biological systems? And what we found was absolutely amazing. And honestly, it blew our minds. So a lot of this work was done off of Hawaii and the North Pacific subtropical gyre, a system that's often thought of as this biological desert. But what these corals told us was that even just a couple hundred years ago, during the Little Ice Age, so about 14 to 1800, this oceanic desert was actually teeming with biological production, teeming with fish, whales, seabirds. It was a fundamentally different ecosystem, even just a few hundred years ago. But since the onset of the Industrial Revolution, we can see a chemical fingerprint of changes in nutrient cycling, so changes in nitrogen signals, changes in CO2, changes in temperature that have fundamentally altered that ecosystem, driving it to a system that we know of today as this sort of biological desert, teeming with bacteria and microorganisms rather than these large consumers that we think of in productive coastal systems now. And what was really fascinating about this study is that we found that these changes took place over the course of decades, changes that in earlier records took thousands to even tens of thousands of years to do. We have now seen happening over the last 100, years. So that rate of change is just mind blowing. And so I'm sure you've heard of a number of different environmental changes that, are happening all around us as a function of climate change. You know, some places are getting warmer, some places are getting cooler. We have changes in the frequency of major storms like hurricanes. As waters warm, we get rising sea levels as land ice and glaciers melt. As CO2 gets into the ocean, it reacts to form an acid and actually increases the acidity of oceans. So it's actually dissolving creatures that have calcium carbonate or chalk like skeletons. So corals and clams and shrimp. I don't really want to focus too much on the doom and gloom of this because honestly, I think all of us have been plenty exposed to the challenges that we face as our oceans warm, as our atmosphere warms, as our uh, growing regions for crops shift out of the places that we have infrastructure built to raise those crops. But I do want to share a example of some of the work that we're doing, trying to understand how these environmental and climatic changes might influence the world around us. And so this is some work that my group is doing in Antarctica, using penguins as canaries in the coal mine for the health of the Southern Ocean. This is a system in Antarctica that's warming about 5 times faster than the global average. And so it's an area that we can look to see how ecosystems are responding to environmental change. And so this is myself out setting up a habitat camera. Antarctica is one of the most amazing places that I've probably ever been to. But you can imagine it's pretty challenging to get there. I can't, it takes a number of flights and a long oceanographic cruise from Ushuaia, the southern tip of South America. We can't spend very long there. One, it's expensive, but two, I would miss my family dearly. And as you can imagine, in Antarctica, the weather does not permit human inhabitants all year long very well. I've gotten quite used to the rather balmy conditions of Rhode Island, and I'm not sure I would want to spend my winters in Antarctica. But there's a lot of really fascinating biology and climate going on, even when we can't be there. And so what we've done is we've set up these cameras all over the Antarctic that look at penguin colonies and the surrounding environment. And what they do is they actually take images. Ooh, PowerPoint crashed on me. That's exciting. Let's try this again. 1 second. Let's try sharing one more time. All right. Let's see if this works. So what we've done is we take images every 15 minutes all year long. And so this is just a time series. And what we can do is we can stitch these images together to understand how these systems change. When do our penguins leave and go off to forage in the open ocean? At what point do they come back? How many nests have they built? How many pairs are there, breeding pairs? How many chicks are there? How many of those chicks fledge and survive to go off to be adults? And so, as you can imagine, we have almost 100 cameras set up all over the Antarctic. They take pictures every 15 minutes. So every year we get something like 2 million photos of the biology and environment of Antarctica, which is arguably way more photos than I could ever possibly process myself. And so what we've done is we've actually set up a citizen science website called penguinwatch.org. And if you're interested, you can actually go to this website and you can become a citizen scientist. You can register, and help us process these photos. And so what you would do is you will see images. And so this image, for instance, asks questions like, for each of these animals, select it and then click on its center. So you'd click on, how many adult penguins do you see? And you go through and you can click on the adult penguins. How many chicks? How many eggs? There'll be questions like, do you see ice on the ground and snow? Do you see, are there other predators? Uh, and what we can do is we can then stitch all of these data together to help us paint a picture of how this environment is changing, how the ecology of these organisms responds to shifts in climate. So the very first day that we had this website fully up and operational, uh, people all over the world signed on and were able to process more photos than I had done my entire year beforehand. So this is an incredible opportunity to make really impactful research happen for us. And what we can do is through this program, we can actually monitor how changes in things like our penguin populations through time. And we found that some of our penguins have really struggling as our oceans have warmed. These tend to be species like our chinstrap, adelie, the very famous emperor penguins and macaroni penguins. These are all ice specialists. These are penguins that either feed on things like krill that like to eat algae on the underside of the sea ice, like our chinstraps and adelies, or they feed or they reproduce on the ice itself, like this emperor penguin. But at the same time, there are some species of penguins that actually are thriving and responding really well. Our gentoo penguins and our king penguins have actually seen massive population increases as a function of warming. These tend to be more sort of sub-Antarctic species. They're generalists, so they are happy to eat anything that swims by that they can fit in their mouth. And as a result, they're capitalizing on this environmental instability. So they're actually doing quite well. And so this allows us to help develop more adaptive management strategies to cope with these environmental changes. So I'm sure we've heard plenty about the sort of the doom and gloom of how our future environment is potentially going to change. We've heard stories about changes in food production, changes in water availability. We've seen the massive increase in frequency of hurricanes and wildfires in California, but it's not hopeless. And I think that message sometimes gets I think that message gets lost in our communication because we as scientists and science communicators, we want to make it really apparent, how serious it is and how much work it will take to make a change. But I do want to make sure that we understand that there is a positive future in sight, and we can get there with the technology that we have today. And so for the last little bit of this talk, I just want to highlight some of the strategies that we've developed to help create a more positive climate future, one that works for all of us. And so the first thing I'm going to talk about is adaptation. And this is something that we all are going through as we speak right now. This is adjusting our lifestyle and our infrastructure to respond to climate risk. So we've already seen about a 1 degree warming since the onset of the Industrial Revolution. And with that comes environmental change. So we are going to have to adapt to those changes. And so adaptation is things like cities and in communities in low-lying areas moving infrastructure to higher ground, potentially coastal fortification, changes in our agricultural and land use practice to adapt to these shifts. Looking at Rhode Island at a glance, in Narragansett Bay, water temperatures have risen by just over 1 degree Celsius, about 3 degrees Fahrenheit, since 1960, significantly faster than the global average. We've seen an increase in both the mean and extreme precipitation. And we've actually already seen about a 10-inch rise in sea level since 1930, again, which is faster than the global average. And so we have developed infrastructure to respond to this current and emerging climate shifts. This is a photo from the massive flooding event in March of 2010 in the Warwick wastewater treatment facility. And as a response, they elevated their levee by about 6 feet to respond to the impending increase in sea level rise and the increase in frequency of typically these 500-year storms that are happening more and more frequently. There's actually a really cool tool, and Martha McConnell, who's a lecturer, a fantastic lecturer at the University of Rhode Island with us, and has given talks with the Aquatic Land Trust before, turned me on to this. And I think this is a really great tool called RI Storm Tools. There's a website down here that you can go and look at, and you can actually play around with future climate scenarios, and you can see what would our sea level rise do to our coastline, and how would it change our cityscape and our infrastructure going forward. We have other really important adaptation tools. At the University of Rhode Island, we have a major hurricane modeling group that is developing high-tech new forecasting systems for hurricanes. One of the most devastating impacts of hurricanes is the timing at which they occur. And so if we have an increase in lead time before hurricanes make landfall, we can make adaptations, we can make adjustments to significantly reduce damage from hurricanes. And so one of the ways we're adapting to this increase in the frequency of major storm systems like hurricanes is through modeling efforts to help us with predictions of when they will occur, their tracks, and where they're going to make landfall. Another example of shaping our infrastructure to match impending climate change. This is some work that my group, so this is me in the center here, and folks in my lab, they're interested in climate impacts on regional fisheries. So this is a figure that shows changes in the distribution of important commercial fisheries along the US East Coast. So here we are up in Narragansett Bay. These colors represent a couple of major commercial fisheries sources. So in green here, we have black sea bass, which was historically found down in the sort of mid-Atlantic bight area, sort of Virginia, DC, North Carolina. These lighter colors represent the center of distribution back in the 1960s. As the color gets darker, we move towards today. Same thing here, we got our American lobster. In the 1960s, it used to be very abundant here off of Rhode Island, and there was a booming lobster fishery here. But as waters have warmed, these species have migrated north to stay in their preferred environmental habitat. And so as waters have warmed, our American lobster population off of southern New England has totally crashed. There's a massive reduction as lobsters are moving up into the Gulf of Maine, where they're now seeing this booming lobster population. At the same time, a new and commercially important species, the black sea bass, has made its way into southern New England waters. And so this is actually some work we're doing in the front. These are all black sea bass. In the back, these are all Atlantic cod. And we're interested in seeing how these two sort of top predators in the system interact as we've got our iconic local cod getting declining as black sea bass increase. But one of the adaptations that we've seen is that black sea bass actually love to go into lobster pots. So as lobster fishermen have seen a decline in their lobster catch here off of Rhode Island, there's actually been a massive increase in the commercially and recreationally viable black sea bass. So there's been a shift in resource use, making good with existing infrastructure to capitalize on a new available market. And interestingly enough, the development of offshore wind turbines, here I'm showing the Block Island wind turbines, has created these artificial reef habitats where it actually creates this massive production system around these turbines. So there's been a huge increase in black sea bass here. And so this is potentially a seed population for regional fisheries around. But obviously, we don't want to just accept our fate that climate is going to, continue to change. There's some very serious future impacts coming our way if we don't reduce and eliminate our CO2 input into the atmosphere. And so the second strategy I just want to mention is talking about climate mitigation. And this is designing and activating policies to control or mitigate the emission of pollutants like greenhouse gases that affect our climate. So I often get asked about what we can do personally to help reduce our CO2 input. And there are a number of valuable things that we can do. Some of the easiest things like upgrading our light bulbs to energy efficient, light bulbs and appliances are actually a net positive financial investment because it reduces our energy use costs. So there's a benefit to us individually, and it is a small but invaluable decrease in CO2. We can switch to a more plant-based diet. So changing our agricultural infrastructure is led by consumer choice. We can switch to environmentally friendly cars. Electric and hybrid cars are rapidly increasing in their efficiency, in the distance that they can drive, in our battery recycling programs. One of the biggest impacts that we as individuals can have is determining our family size. And this is actually a conversation that my wife and I have had as we've talked about, how many kids we see in our future. Thinking about the climate impact of our growing population is probably one of the largest ones. But I just want to say that I think probably the biggest individual impact that any one of us can have is to educate ourselves and to vote. And so we should be proud living in Rhode Island because we are leading the way in climate change education in the nation. This is the State of Rhode Island General Assembly from 2019 requesting the incorporation of education to develop a key set of environmental and climate principle concepts to be infused in all subjects K through 12 in public schools. It means educating ourselves and voting for people that take science seriously and use that science to develop policies that push us in a environmentally friendly direction. There was recently an open letter written to newly elected President Biden for over 408 businesses and investors, valued at over $4 trillion in annual revenue and another trillion in asset management, have supported major financial and technological advancements to reduce CO2 emissions. Places like major transportation groups like Ford, Energy and Power, General Electric, National Grid, Johnson and Johnson, Pfizer, etc. But the real change comes at the national and international level. And the real change that we are going to see in the reduction of CO2 is going to be through major international cooperations like the Paris Climate Agreement, which has set a goal of reducing CO2 emissions to keep warming below about 2 degrees Celsius. Some of the major outcomes of this Paris Climate Agreement is that it strengthens climate actions every 5 years. It has major climate finance support systems in place, particularly to help subsidize developing countries to make sure that they can keep up with changes in climate-friendly infrastructure, enhanced transparency, and long-term goals to set net zero CO2 emissions. And so there have been over 187 countries that have shared national climate action plans, and about 10,000 new climate initiatives. That includes over 127 million hectares of degraded land in Africa and Latin America being restored to increase CO2 capture, about $1 trillion in solar investment to mobilize new green energy, and 20 countries that have doubled clean energy R&D in the last 5 years. And so this is a little bit of a busy slide, but I just want to call your attention to this carbon stabilization wedge website down here, which is a really cool way to explore our path to net zero climate emissions. And so what it does is, here's this figure. It's got year on the x-axis, amount of CO2 we produce on the y-axis. This squiggly line is what we've done so far. This top line here is what we call business as usual. This is our current path. This is, if we don't do anything new, this is what CO2 is going to continue to do going forward. What we want to do is by the end of the century, and perhaps even sooner, we would like to get to net zero carbon emissions. So we are no longer putting in additional CO2 into the atmosphere. And that's kind of a daunting task. It requires about a 6 or 7% reduction in CO2 emissions every year. And so what climate economists and scientists have done is they've broken this goal up into these wedges. They call them carbon wedges, which represents about 2 gigaton reduction in carbon per year from existing technologies. And so things like decarbonizing our power, so removing fossil fuels from power, like wind and solar, switching to carbon capture technology in coal plants, changes in transportation, vehicle efficiency use, building energy efficiency, reducing deforestation or promoting afforestation. And so what we see is that with only existing technology, things that we have at our disposal today, that goal of reaching net zero climate emissions is realistic. It's got this reality check where it has algorithms to determine the amount of population change, financial investments, and a whole host of things that control how feasible these changes in our CO2 production are. And you can actually get to net zero carbon emissions only using existing technology. We don't need some magic future technology that to be developed sometime in the future. And there's some real positive benefits to switching to renewable energies. This figure just shows time on the x-axis. In orange is the price of the solar panel per watt of energy, about $101 back in 1975. As we go forward in time, solar power, the cost of solar declines, usage goes up, price declines, and we get what we call this virtuous cycle. And so we actually get a net positive financial increase as we switch to more renewable energy. One of the questions I get a lot about is, how realistic is this? This figure that you see here going through time, and it's going to cycle through again, is the change in CO2 emissions by major countries last year during the COVID pandemic. So the dark colors are basically no change in CO2 emissions. The lighter it gets, the more bright blue, the higher the reduction in CO2 emissions. So here we start in January. And as you see, as we move through time, we actually, during this pandemic, had massive reductions in our global CO2 emissions. In order to hit our end of the century targets, we need about an annual reduction of 6 to 7% reduction in our CO2 emissions. Well, during 2020, we actually saw our target 7% reduction, even more in some places like the US and the European Union. And while obviously having to be in a global pandemic and major lockdowns is not going to be a viable pathway forward, I'm a glass half full kind of person. And what I see in this is that actions that take place today, in one single year, can have realistic major changes in our CO2 production. And this is largely with no major change in technology to promote new renewable energy. This was largely a reduction in energy use and a reduction in things like transportation. So imagine what could be possible as we develop our economy again and get ours going again, if we do that in the guise of switching to more renewable energies. The last thing I want to mention is there are major co-benefits to switching to renewable energies. A co-benefit is just a solution uh, to climate that has additional positive outcomes. And so this is a quote from Dr. Maria Neira, who's the World Health Organization Director for Public Health. And she said that the health burden of polluting energy sources is now so high that moving to cleaner, more sustainable energy choices for energy, transport, and food systems effectively pays for itself. So when you take health into account, climate change mitigation is actually an opportunity, not a cost. And so just crunching some numbers from 2007 in the US, where we had a very little large scale renewable energy, to 2015, where there's an exploding market in both wind and solar power. It's estimated to have resulted in about a 7,000 reduction in premature deaths, $56 billion in saved public health benefits, and another $32 billion saved in avoided climate costs. So I'm just going to end with this sort of key on insights to how we off-ramp greenhouse gas emissions. And the take-home messages I hope you get are, one, no one person or even one country can do this alone. This is a global problem, and it's going to require global solutions. We're going to need actions in many sectors of our economy and infrastructure. So I call that the silver buckshot approach rather than the silver bullet approach. But we can do it. We can avoid those worst case climate future scenarios with the existing technology we have. And there are numerous co-benefits that actually make it a financially positive investment. So with that, I'm gonna stop sharing my slides. And I wanna open this up to questions. I wanna say thank you all for listening. I hope that you found this valuable and learned something. And I'm happy to answer questions as we think about our future in this changing climate.
Dr. McMahon, I would just like to say on behalf of the Aquidneck Land Trust and our funder, the Donner Foundation, we really appreciate your lecture this evening, especially on Earth Day, Earth Evening. And I appreciate your message of hope rather than keeping it doom and gloom. So thank you very much.
Yeah, my pleasure. Thanks so much for having me. Can I answer questions? It looks like in the chat, Nina had a question for electric vehicle batteries, concerns about sources of material, labor, conditions, safety materials, disposal. Yeah. So I'm happy to chat about that. One of the things that we're going to have to remember is that there are no actions that we are going to be able to take that are devoid of trade-offs. As I talked about, and I'll get to your specific question in a second, but as I talked about, switching to, say, renewable energies, there are a lot of our infrastructure and economy is built around a fossil fuel system. There was a major decline in coal development and usage in Alaska a few years ago, and in that decline in coal price absolutely crashed the Alaskan economy. And so we have to be cognizant of all of the trade-offs that come with these changes. And so development of batteries requires mining of ore and minerals. There's been changes in mining practice, particularly in seafloor beds, to get precious metals that we use in a lot of our electronics and our batteries. There are challenges with battery storage. Batteries don't last forever. And so part of the challenge we have is going to be balancing those trade-offs. And so there are a couple of major benefits to making that initial investment. Is that one, as we invest consumer resources and demand into new technologies, it absolutely accelerates the technological advancements in efficiency and safety. We've seen that in our solar and wind power. We see that in the development of even things like hybrid vehicles. You think about the battery, how long a battery lasted in a Prius, 15 years ago to today. It's uh, it's amazing the developments that we can get when there's consumer demand behind it. And so that doesn't mean that we're off the hook. It doesn't mean that putting up wind turbines will have no impact. It changes, uh, migration patterns of birds. It has impacts on the noise scape of the coastal system that can alter the migration pathways of, whales and other marine mammals. So part of our goal as scientists is to quantify and develop algorithms and metrics to weigh those trade-offs. But when you think about the long term, in long term, I mean by like 2050, changes that are coming with the increase in CO2, uh, basically all climate scientists agree that the investments that we need to make now will outweigh the benefits that we get from these investments we make now are going to outweigh those negatives on the net front when we think about changes in our food infrastructure, changes in our health, etc. But that doesn't mean that there won't be potential trade-offs and negative consequences, and it doesn't mean that we are off the hook on developing more efficient, safe technologies.
I have a quick question.
Yeah.
Hi, Kelton. Thank you so
Hi,
much for
Micah.
giving this talk this evening. It was really fantastic. And actually, I don't know all the details of your work in Antarctica, so it was really terrific to see more of that. I was wondering if you could offer some more remarks about that relationship between sea bass or lobster, or perhaps what the forecast is. I know there might be some fishermen or recreational fishermen that are on the call right now, and what if you even have enough data on what might be to come.
Yeah. So, I mean, so we certainly have seen a substantial increase in black sea bass population in the last 10, 15 years. We actually find black sea bass all the way up into the Gulf of Maine now. And so as waters are warming, they're moving northward. And as I mentioned earlier, and anytime you listen to me talk, you'll hear me talk about trade-offs because I think it's vital that we really quantitatively and carefully think about trade-offs for all of our actions and all the future changes that current and future changes. And so one of those challenges that fisheries managers are weighing is the potential benefits and the potential drawbacks to this shift in black sea bass population. They are demersal, or sort of bottom dwelling upper trophic level, so high in the food chain predators. Uh, there's concern that they may be coming in and feeding on lobsters and crabs, which are both very commercially and ecologically important species in the area. I had a master's student, Nina Santos, who actually just defended her master's in December. And her project was looking at the diet of black sea bass and cod in southern New England. And she found that they were targeting decapod crustaceans, so cancer crabs like the Jonah crab, which is another sort of climate winner, in this area, whose population is increasing. And so there is concern that the increase in black sea bass in the area may further exacerbate challenges we have with declining, crab or lobster populations. Right now, we're facing a challenge where the current catch quotas for black sea bass, they're regionally distributed, and they're based on the historic population distributions. And so the vast majority of the sort of center of black sea bass biomass, the population, is largely in this mid-Atlantic region. And so they get the majority of the annual catch quota. Actually, just this year, I believe, we saw the first significant shift in catch quota for southern New England fisheries. And so the challenge they were facing is, you know, the mid-Atlantic states get something like 75% of the total allowable catch, and we get about 25%. But as climate has shifted the population, now we actually have way more black sea bass than we used to. And so as fishermen locally are vying to get an increase in that catch quota, it would mean reducing catch for the fisheries in the mid-Atlantic. And so their economy, their infrastructure is built around, this historic value. And so there's trade-offs that these fisheries managers are playing, thinking about how we set the catch quotas based on our, jobs, economy, the food needed versus what climatic and environmental conditions say, about population dynamics. And so as a fisheries scientist, my group helps provide scientific data to help managers make decisions like that. Other questions? Let's see. Alan had asked why the media doesn't cover some of the stats that I've presented. I think part of that will be depend on what media sources you look at. So I have, uh, as you could tell, I like to talk, and so I have a much longer presentation that I've been painstakingly trying to pare down for you. But I had a number of media outlets that and videos that I can share with you if you're interested. The BBC and NPR, I think, does a really nice job of covering very science-based research on climate. So it depends on where, some of it will depend on where you get your media from. Some of it depends on the sort of the goals of the target stories. Remember, media is sort of a catch-all term for the sharing of information and content. And so I think going to accredited sources for the science is one of your best bets for finding this information. Coming to climate seminars like this, I think, is a great way to hopefully bridge that gap between the scientific information and the science communication of it. And if you'd like, I included my email in this, but you can also, Kelton McMahon is luckily a fairly unique name, so you're welcome to reach out to me, and I'm always happy to chat and share resources. I try to include all the citations to the literature that I've shared today, but yeah, as I mentioned, I'm always happy to talk science, climate, the world around us. Let's see. Do we know what caused the CO2 increase 3 million years ago? That CO2 increase has to do with large scale, they call them Milankovitch cycle processes. So major changes in, things like Earth's tilt and wobble and orbit, things like that, which we've seen before, but take place over hundreds of, 100,000-year timescales. And one of the biggest challenges we have now is time to adapt. And so I always like to use the analogy of a hurricane. If I were, if we get a warning that in a week a hurricane is coming up from Florida and it's going to hit Newport, it gives you time to adapt, right? We can board up our windows, we can bring, our furniture in from outside, we can get ample food, water, we can fill up our bathtubs with water, we can get extra batteries and headlamps, we can make sure we've got plenty of fuel, for our gas stove, whatever, right? If a hurricane hits us instantly without any warning, the damage is going to be substantially worse. And so you can think about that on sort of climate time scales with, if you give the environment 100,000 years, organisms can adapt and respond better than they can if you change something in decades or 100 years. And so one of the big challenges that we're facing right now is the rate of change. It's not that the environment has never had CO2 levels like it has today, but in our records, we have not seen this rate of change, how fast it's changing. And it's also important to remember that the environment is going to respond and adapt. It's not like the Earth will implode as our climate shifts, but what we have is infrastructure built around the current climate. The bread belt in the middle of America, the agricultural growing centers in California. All of that infrastructure, the knowledge, the know-how, the resources, the farming land is built for a current climate band. And so if we rapidly change climate, it rapidly shifts where those bands are. So it's not that we couldn't grow crops, but southern Canada is not built to have agricultural land the way that Southern California is. And so while it is absolutely true, like 3 million years ago, we've seen CO2 conditions like we've seen today, we've seen temperature like we have seen today. We weren't around 3 million years ago, and we didn't have infrastructure built into the current climate bands. And so it's that rate of change that is what makes it so much different than what it was during the Pliocene 3 million years ago. Other questions? Well, if we don't have more questions, I guess I will say thank you so much. I will just note that there's a recent BBC report, if you'd like to look it up, that talks about climate futures in sight, and it has a really nice message. I was a little afraid on my time, so I didn't share it, but it's got a really nice message about recent climate reports that have shown the substantial increase in climate pledges in countries like China and the U.S. That actually put our 2050 climate goals within reach now. And that's not a story that I would have been able to share 3 months ago. And so things like that give me hope. And so I hope you'll take that message of hope with you into your evening as we finish off another Earth Day. So thank you so much. I really appreciate your time this evening. And I hope to be in touch with some of you again in the future as you have questions.